Transformers are simply devices that convert one voltage to another. Transformers are found everywhere from power distribution centers to the plug in your cell phone. For example, power plants have electrical generators that produce high voltages of alternating current that must be transformed before using them in your house. A typical transformer consists of a laminated iron core. The lamination of the core is simply to reduce any eddy currents that may form within it. Around this core are two separate coils of wire. An electric generator is overproducing AC electric current somewhere to the left. Remember that alternating an electric current will create a magnetic field around the conducting wire. This magnetic field is then able to travel through the iron core to the other side. On the other side, we have a secondary coil. When that changing magnetic field travels through the loops of wire in the secondary coil, there is a change in magnetic flux. According to Faraday's law of induction, this changing magnetic flux will induce an EMF inside the secondary wire coil, creating an alternating current. Connected to this wire loop is some sort of resistor. This is the goal, really, to deliver electric current to some device. Faraday's law of induction tells us that the primary voltage is equal to the negative number of turns on the primary side of the transformer times the change in magnetic flux produced on the primary side divided by the time. We can do the same thing on the secondary side, where the voltage is equal to the negative of the number of secondary turns times the change in magnetic flux on the secondary side divided by the time. Typically, we are looking to see how the primary voltage compares to the secondary voltage. So we are really just looking at a ratio. Now, since everything is connected by the iron core, the magnetic flux as a function of time on the primary side will be equal to the magnetic flux on the secondary side. Cancel out the negatives on both sides, and we end up with a beautifully simple equation that tells us the ratio of primary voltage to secondary voltage in a transformer depends on the number of turns on each side. So the side that has more turns in the wire will have a higher voltage associated with it. Makes sense, since the side with more turns should be more sensitive to the change in the flux due to the higher area affected by the magnetic flux. The output voltage of a transformer can be either more than the incoming voltage or less than the incoming voltage. If the voltage decreases across the transformer, we call it a step-down transformer. But if the voltage increases, we call it a step-up transformer. Say we have a portable X-ray unit that has a step-up transformer. The 120 volt input of which is transformed to 100 kilovolt output needed. The primary has 50 loops. How many loops does the secondary need? We can use our transformer equation here to set up that ratio, since we know both voltages in one of the loops. As always, we pay attention to our units and make sure they are the same so we can do the math, and we get the secondary loop having 41,700 loops. So what is the current output of this system if the secondary coil draws a current of 10 amps? We can go back to our transformer equation and look at how the current and voltage relate to the number of coils in our loops. Assuming there is negligible resistance within the system itself, we can say that the electrical power input of a transformer is equal to the electrical power output. And since power is simply the current times the voltage, the primary voltage times the primary current is equal to the secondary voltage times the secondary current. This is nice because we can relate those two things within the transformer. Pay close attention to the subscripts here. The ratio of the secondary voltage to the primary voltage is equal to the ratio of the primary current to the secondary current. This allows us to relate the current back to the number of loops in each coil. With a little bit of algebra, we can determine that the ratio of secondary loops to primary loops is equal to the ratio of primary current to the secondary current. We can actually solve this problem in a couple different ways. We can use our voltage to current transformer equation, or we could use our loops to current ratio. It doesn't matter because both will work out to be 12 milliamps. So a transformer is a device that changes the magnitude of AC voltage across a metal core by changing the magnetic flux. It consists of a primary coil that induces voltage into a secondary coil. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil equals the ratio of the voltage in the primary coil to the voltage in the secondary coil. The turn ratio is also equal to the current in the secondary coil to the current in the primary coil.